Now, how does this lighting happen? We have seen that intra-cloud, inter-cloud, cloud-to-ground, three types of lightings we have classified. But how does it happen is the important question that's facing us today. Now, the important point to note is that solar energy is the main energy which does all this phenomena possible. The solar energy heats the Earth's surface layer. It evaporates the moisture from this Earth's surface, and this moisture enters the air layer in contact with the Earth's surface. So we have got a moisturized air in contact with the Earth's surface. Now the Earth's surface also Earth's surface also heats up the air in contact, and of course the moisture which is inside that air. Therefore, now we have got air plus moisture which is hotter than the upper regions. And then also invariably there are very fine dust particles present everywhere in atmosphere. They are known as aerosol particles. Very fine dust particles are known as aerosol particles. So on top of the Earth's surface, which is heated adequately, we have got hot air plus moisture plus aerosol particles. This moisture plus aerosol particles and hot air, because they are hotter than the air above them, it starts moving up. It starts moving up and up. We call this the updraft. So the updraft contains hot mixture of air, moisture, and aerosol. As it moves up, we know that the temperature drops down continuously. It was shown earlier in the troposphere. Temperature goes down from Earth's surface to 0 degrees, nearly around 2 to 3 kilometers above Earth's surface. So as the updraft moves up and up, it gets cooled down. The moisture starts condensing when it approaches 0 degrees centigrade level. That means approximately 2-3 kilometers above level, moisture starts condensing. It condenses, of course, into very, very small ice or water droplets. They are known as super cooled water droplets, very, very fine droplets. They're also very likely to be thrown up, rather moving upwards. So what we have above the 0 degrees centigrade is, in addition to normal moisture, we have got moisture plus small amount of condensation into water. Here I must point out one very interesting thing. Suppose we have got absolutely pure water, absolutely pure, no dust particles whatever. When does it freeze? The question is very easy, one may think. It's not so easy. The temperature at which the pure water freezes is around -30 to -40 degrees centigrade. It is not 0 degrees centigrade or 4 degrees centigrade. It's because of the presence of these aerosol particles. When we cool down to approximately 4 degrees to 0 degrees, the moisture starts settling around these dust particles, and that's how the condensation starts and goes further. If there are no dust particles, the freezing takes place only around -30 to -40 degrees centigrade. So now we have got around 2 to 3 kilometers height in updraft containing hot air, moisture with some amount of condensation, and then aerosol particles. Now this continues as we go further and further up. The very, very fine water droplets, they grow in size. The surrounding moisture settles on the superfine water droplets. They grow into larger and larger drops. And then the temperature goes down much below. As you go further higher up, they will freeze into small icicles. Initially icicles, very small ice particles, which grow into what we call hailstones. So we have got now superfine water droplets, larger water drops, icicles, and around 14 kilometers hailstones are there. Now, once the large water droplets and hailstones become sufficiently large, the gravitational force attracting them downwards will make them fall down. So now the cloud has got an updraft consisting of hot air, moisture, aerosol particles, and icicles, slightly condensed moisture going upwards, and then downward moving large water droplets, supercooled water droplets, and hailstones. They are coming down. So it's a very interesting picture within the cloud. It is shown here. The red letters show the mixture that's coming down, hailstones and large supercooled water droplets. Upward, we have got various levels of moisture, fine drops, dust, and then less moisture, more water drops, then water droplets here, and then more and more icicles, supercooled large water drops, dust again, hailstones and large supercooled which are coming down. Now this formation of upward and downward drafts gives the main zone of electrification, which takes place mostly in this region, where these two are mixing in a very, very rapid manner. The electrification takes place here. Now, as I told you, many theories have been proposed over more than a century how electrification occurs in this mixture of upward air draft, moisture, supercooled water droplets, air, downward large water drops and hailstones. Now, Simpson's theory, Elster-Geitel's theory, Wilson's theory, go on. In fact, I think Madame Curie also has developed some theories of Uppsala University. He is very much there, active in University of Uppsala even today on lightning itself. Now, no one theory is adequate. Therefore, we will not try to go into the theoretical aspects of that. Some of them can go into quite a bit of mathematics. Therefore, I will rather avoid going into those things. What we have is this important feature is the cloud top essentially becomes positive. Top zone is not a point. Top zone becomes positively charged. The middle to almost bottom gets negative charged, and then as we go down towards the bottom of the cloud, the negative charge concentration becomes more and more. It is shown in this figure 5. So you'll see I have just drawn a line in the middle, but there's nothing rigid about it. You'll see the top half, top zone. I'll not call it top half, it is the top zone. Is having a larger percentage of positive charges and some amount, very small amount of negative charges. And then bottom zone has got a much higher concentration of negative charges and also some positive charges. And the most important thing for us to note is that the negative charges in the bottom cloud attracts positive charge from the air surrounding, and there will be a zone of small positive charges present here. The zone of positive charges below the bottom of the cloud and the high concentration of negative charges within the cloud, they are the most important from the point of view of initiation of a lightning. Now, the question is, how does the lightning get initiated? Now, the typical electric field required for breakdown of air into a spark or an arc, whatever it is, at the Earth's surface is approximately 27 kV DC per centimeter, or approximately 3 kV per millimeter at the Earth's surface. However, inside the air, we find that the electric field intensity is only of the order of about 10 kV per centimeter to about 4 kV, maybe 1 kV to 4 kV per centimeter, which is very, very low. So discharge cannot happen within a cloud. Therefore, more recently, there has been photographic evidence also. Lightning gets initiated in the bottommost region. That's what I mentioned to you here, in the bottommost region, what they call bi-directional leaders. We'll talk about it presently. We'll go further now and see how it goes on. As I mentioned to you, the field within the electric field within the cloud is 100 kV per meter. That means 1 kV per centimeter to 2 kV per centimeter on the average. And it can go right up to 4 kV per centimeter as shown here. But this is not at all adequate for breakdown to occur. Now, recently, field photography has shown that streamers or electrical discharges. I will explain to you what streamer and what's the leader a little later. The streamers, that means discharges start between the bottom zone of the negative charge the positive charge zone immediately below the cloud bottom. As I shown you in the previous figure, that's the figure 5. This is the bottommost region has got some positive charges induced by the negative charges at the cloud bottom. Discharges start occurring between these two. And because they are spread horizontally, these discharges spread sidewise, maybe even up to 100 kilometers. Not a small distance, not a small distance at all. So these discharges spread in both directions because they are both horizontal. They are spread in both directions. They are therefore known as bi-directional leaders. Now there's a small distinction, important distinction between what we call a streamer and a leader. In a streamer, the development of electrical discharge is due to ionization by the electrical field. Mainly, the electrons collide with the neutral molecules and then cause an electron to get ejected. So that will create an electron-ion pair. This is known as ionization by collision. This is a very well-known phenomena, particularly in hydrogen engineering. It's a very fundamental phenomena, ionization by collision. So this is a streamer where the electrical discharge development is primarily due to the applied electric field and due to collision between electrons and neutral molecules. That's collision by ionization by collision is the prominent phenomena. On the other hand, once this current density in the streamers become very high, there will be high temperatures developed. In high temperatures, there will be thermal ionization, and that becomes much more prominent than the ionization by collision process. This is known as a leader that can develop by itself, providing the electric field is adequate for its propagation. That's a leader. So this is a distinction between the streamer and the leader. Now, as I told you, between the negative charges of the cloud bottom and the positive charges of the below the cloud bottom, these streamers develop into what we call bidirectional leaders. Now, one end of this bidirectional leader, essentially the negative end, starts developing towards the earth. So one end of the bidirectional leader starts developing towards the earth. Now, this is the initiation of the lightning. This leader moves towards the earth. That's the most important point. Now, why does it develop as a one shot to the earth? No. The reason is the moment this leader develops over a short distance, the charge density at its tip falls below the level that's necessary for its development further. So what happens is that it will wait. In this waiting period, very short time, they're all in sub-microseconds. 1 microsecond is 10 to the minus 6 seconds. Sub-microsecond time is required only for the parent cloud to feed the charge into the tip. And once the tip is fed with electrical charge, the electric field at the tip increases and it progresses further. So this is what we call a stepped leader. So earlier, people thought the development of the leader takes place within the cloud like this. But more recently, as I told you, photographic evidence, which I think I have got photographs of that also, is between the positive region and the negative regions here. They develop into bidirectional leaders shown here, and that develops towards the earth. Remember, this is the negative charge. Now, there's a very interesting question which may come up in your minds. Because of the normal electric field, the charge on the earth surface is negative. So how can this negative charge come towards the negative charge? We know very well by Coulomb's law, like charges repel each other. So how does it develop? It's a very interesting question. The lower ionosphere has induced negative charge all around. The charge density I have told you is approximately 10 to the minus 9 coulombs per meter squared. But as the negative charges gather in the cloud bottom, that induces a positive charge on the Earth's surface. Please remember this again. It is worth repeating that. As the negative charge develops within the cloud bottom here, that induces a positive charge on the Earth's surface below the cloud. So elsewhere, far away from the cloud, the Earth charge density will be negative. But right below the cloud, the charge density on the Earth has turned from negative to 0, 0 to now positive. So now we will see that the streamers are facing they are getting the charge fed from the parent cloud. Negative charge is fed to the step leader, and then the positive charge is there on the earth to attract it, so it starts developing downwards. As I told you, this development is only in steps. The reason again I will repeat, it's worth repeating that when the charge is sufficient, when the electric field intensity at the tip of the leader is sufficient, it develops further down. But as it develops down, the charge at the tip comes down. The electric field intensity at the tip therefore comes down, and therefore it cannot propagate further. It holds. In the meanwhile, the huge negative charge available in the cloud bottom, right up to 100 coulombs will be there. So that is fed to the tip through the conducting channel of the leader, step leader. And then once the step leader gets this charge, the electric field starts building up once again. Once the field comes up to the required level, there will be further breakdown. So it takes the next step. So this leader towards the earth develops in steps. Now, just a small deviation, whether it's intra-cloud discharge or cloud-to-cloud discharge or the cloud-to-ground discharge, the development is always in a stepped way, stepped leaders. So when you observe lightning, you would have seen it's not a single line. It goes up in steps, sometimes very, very crooked also. Why is it branching off? That's another important, interesting question. Why is it developing into steps like this? Now, supposing it has come to a certain point, any one point here. Now, at that point, it will see the air all round. The electric field density for breakdown of this air all round will not necessarily be the same. The electric field breakdown strength for the air will be different in different directions because the air is not as homogeneous as we think. But at the minor level, at the sort of very small level, the electric field density will be different. So breakdowns can occur in a very different direction from the previous step. Therefore, it can develop into this direction, and sometimes the breakdown can take place in multiple directions also, because in the multiple directions, the electric field strength of the air can be weak. Therefore, it develops in multi-directional ways. So now you will see that what we have seen in the real life, what we have seen, most of us would have seen hundreds of times or maybe thousands of times. It develops into many, many steps like this, but on the whole, it starts moving towards a tall grounded object on the earth like this. Why? The question is very easy to answer. Now, as I told you, the negative charge here on the cloud induces a positive charge on the earth's surface also. The same is true of the tall grounded objects. I'm sure you recall that if you have got a large size orbiter-shaped conductor and it is given a charge, the charge density is inversely proportional to the radius of curvature, which means that the sharper points will have higher charge density, and because of the higher charge density, the electric field intensity at its surface will be higher. So now, if you think of a tower, the tallest point of the tower is the sharpest point. Therefore, the electric field intensity there will be the highest, and therefore there will be local streamers. Again, remember streamers, because here the current growth is by ionization by collision phenomena. It's not yet thermal. Therefore, we call it a streamer. Whereas here is a stepped leader. It is temperature dependent there now. Temperature is the driving force in addition to the electric field. Here is only the electric field. It's a streamer here. The stepped leader here. They start moving towards each other. In fact, different branches can move in different directions. There is one more object. It can go towards that also. So as the stepped leader comes down, the electric field intensity becomes higher and higher and higher. The reason is this gap between the positive electrode and the negative electrode becomes shorter and shorter. The potential of the cloud, as I mentioned in an earlier table, can go right up to 100 billion volts. Now, the minimum potential required for a lightning to occur is approximately 2 to 5 million volts. So you can say that the potential at the tip of the step leader may be anywhere from a few million volts to maybe tens of millions of volts. Therefore, as this leader comes down, it's easy to imagine the electric field density becomes higher and higher in this direction. Therefore, it starts going towards it finally, and then attaches it to itself. So we call that a forward leader between the cloud and the grounded object. This is called the forward stroke. It's essentially the step leader coming into contact with the streamer from the grounded object, which completes the forward stroke. I have shown it here. You see that there are two other branches which are very close to ground, so it may attach here also. It may attach here first, it may attach here also. Now, some of the properties of this are very important. The velocity of development of the step reader is about 1/10 the velocity of light, approximately 1/10 the velocity of light. It is relatively slow because it develops in steps. It has to wait for the charge to be fed from the cloud to the tip of the step. Now, once the step leader makes contact with the earth object and the forward stroke is complete, it behaves as a near short circuit between the huge voltage of the cloud and relatively zero voltage there. That means the huge voltage is applied between these 2 points and there is an effective short circuit between these two. Now what happens because of this is a very huge current develops in the same channel, extremely huge currents which can vary anywhere from 4 or 5 kiloamperes right up to 200,000 amperes. That means 200 kiloamperes. And the channel diameter is hardly of the order of 10 to 12 kilometers. The current flowing in that small region heats it up to enormous temperature to the order of about 15,000 degrees Kelvin to almost 60,000 degrees Kelvin, which is comparable to the temperature of the sun's surface. So you'll see that it becomes extremely hot, extremely bright, and then it heats the surrounding air very rapidly because the high temperature, the air expands at a very rapid rate. That's what you hear as the thunder. That's the acoustic effect of the thunder. So we have got first the forward stroke, then the return stroke causing the thunder. Thunder means the sound because of the supersonic velocity of the air expansion in the surrounding area.